All right, so these are going to be the concept of operations for our CubeSat. So first, we're going to launch our CubeSat right here. Then we're going to go to the collect data and power on the light side and oceans. That's one of the functions. The second function is it's going to sleep on the dark side and land. And then the third is the download data, which is going to be on the overground station. And the process is going to be images and sort into useful ones. And we're going to send this to Woods Hole Oceanographic Institute.
System level block diagram for our CubeSat. So the first system is the structure subsystem. So that consists of the acrylic panels to box everything in, and the aluminum rails, which are the bare bones of the structure. We also have the solar panel, which is going to be attached to the structure and consist of part of it, not an integral part, but part of it nonetheless. This is connected to the power subsystem with the solar panel assembly, which provides power and recharges the battery. The battery, in turn, provides power to the Raspberry Pi in the ADCS subsystem. The Raspberry Pi is going to be using data and powering from the IMU and powering it with the power from the battery. The IMU will be giving RPY data, and that will in turn tell the Raspberry Pi when to take a picture, and that's how it's going to go with the imaging subsystem, which consists of our camera. The camera will take pictures on the Raspberry Pi's signal, and it will then give them back to the Raspberry Pi to store on it. The final subsystem we have is the communications, which is going to be connected to our Raspberry Pi and our ADCS subsystem through the Bluetooth on the Raspberry Pi. This Bluetooth will be able to connect to the ground station, and it will be able to uplink and downlink photos and software updates and anything else we need to send to our Raspberry Pi or the ground station. That is it for our system level diagram.
Here's our satellite. As you can see, there is plenty of room inside the satellite for anything more we need to add, as it has the Pi, the camera, the IMU, and the battery situated inside, and there is a large space on top of the Pi to fill. For powering, we have the ability to slot the power cable into the hole at the bottom, into the battery bank, which will then feed power into the Pi. We have confirmed that it can take power from the wall and power the Pi at the same time. We also have the HDMI output ability able to slot through that same hole at the bottom of the sat under the Pi in the current view and go out and connect to a monitor on the ground for troubleshooting. There is plenty of room for the cabling inside, and we've confirmed on our real sat that we can connect all of the items with no issues. The battery is held in place on the left side of the satellite and is held in place by two strips. The battery is held in place by two strips of Velcro on the large side of the battery and one at the top in the current view. This ensures that under launch circumstances, with the camera facing down, so upside down of the current view, rotated 180 degrees, the current view, that the battery is supported by a normal force and all of the screws instead of just a latching force of the sticky Velcro tape.
The SMART goal for the structure section of our CubeSat is really defined by the purpose of the structure. It's there to support all the other components and ensure they can carry out the task that's assigned. Or in our case, so that the camera can take the pictures and then the brain and communications can downlink it to the ground. So given that, for the lifetime of the other components, however long that may be, the structure should withstand all forces without deforming to the point where it inhibits any other subsection of the CubeSat.
To create our mass budget, we experimentally determined the mass of each component to the correct sig figs. Then we compiled each mass into subsystems, and then finally a mass for the final overall system of the CubeSat. The comms, AC/DC, and software were combined because of the intertwined nature, and each system only had one or two components.
I will now be discussing the power budget for our
CubeSat. So the powered components in our CubeSat are the battery, the solar panel, the Raspberry Pi, the IMU, and the camera. The solar panel gains the power, the battery stores it and distributes it to the Pi, which distributes it to the IMU and the camera. So we had difficulties in actually creating a proper power budget because the whole team was at a national chess tournament for 5 days. We all had the SAT, and we couldn't get reliable values in the time we had. But if we were to create a power budget, this is our plan of action. We measure the charge and disk times for the battery, and we would do this multiple times just to make sure, and over multiple cases. We measure the solar panel output in direct sunlight and darkness, well, obviously with 0 and like cloud cover. Find energy consumption of all the energy consuming components during all the states, the downlink, the sleep state, and the photo state. And then we would record and use these as a constraint for the processes. We would also calculate the values in orbit using these and known values such as solar radiance in LEO. And here are smart requirements. The power subsystem must provide adequate power to allow all powered components to carry out their mission unimpeded throughout the lifetime of the CubeSat, and it is done by the demo day. Okay, we're going to be describing our software subsystem. So the smart requirements for this subsystem is the software should be able to read and use all measurements from the IMU to determine its state throughout the lifetime of the CubeSat. The software should also be able to effectively complete all of its tasks when it is assigned them, such as changing states, uplinking photos, and downlinking photos. The software should also be able to be modified during an uplink period and change without any errors. Now let's discuss the architecture of the system. So after this, our gyroscope and all the RPY stuff is manually calibrated and our CubeSat is in orbit, it'll enter the low power state. So it'll be sleeping until it's over a point of interest, which is either an ocean or a ground station. And that is going to be determined by the hard-coded flight plan that we put in the software. Let's discuss this pathway. So when the flight path is over the ocean, it enters the photo ready state. So during this state, it'll continuously check the RPY against the desired RPY continuously, and if it gets a correct RPY, it will take a photo, compress the photo, and return to the photo ready state. And once it leaves the ocean, it will return to the low power state. Another option from the low power state is if it goes over the ground station. If it's over the ground station, it will enter that downlink state in conjunction with the uplink state. So the downlink state downlinks photos with all software power. We're going to stop taking photos at this point because it's most likely that the downlink or the ground station is not over the ocean, and we have a very limited amount of time to downlink our photos, so we want to use all the resources for it. And the uplink state is in conjunction with this, and we're going to be receiving any data that we need to from the ground, such as modifications to the code and stuff like that. And the ground station, when it receives photos, it's going to be really simple. It's going to merge the photos to the GitHub repository, and we can also send things during that time. So here's our development plan. So we're going to implement all the equations from the ADC's lab to calculate the RPY and make sure it takes a photo at the right time. Next, we are going to calibrate this with testing data using our plot.py functions. After that, we're going to hard code the flight path to require less data usage or less power usage, and it'll probably be more accurate since our sensors are not the most accurate. After that, we are going to test on a small scale flight path like in our local area, and then we are going to add a compression functionality, and if we have time or we can do it effectively with our resources, we will also try to recognize like a photo with garbage or not to see if we should delete it, because we do not want to uplink random photos that don't have any use, or downlink random photos to the ground station if they don't have any use. And then we'll do a full test run, fix any bugs that we find, and finally we will deploy it and test it on test day for our final presentation.
The link budget for the CubeSat. We were having difficulty finding the RSSI values between the ground station and the CubeSat, so we weren't able to collect data as quickly. If we were to have, in the coming days, we're going to collect more data so we have a better idea of how RSSI relates to distance and objects in the way, and as well and noise. So, however, with the little data we did collect, we were able to see a pretty good relationship between RSSI and distance, as we see in the graph. as distance increases, the RSSI value becomes more negative. We still had a connection even though we were at the end of our 75-meter long hallway, even though that connection was pretty weak. Some objects we put in the way between the CubeSat and the ground station was a door, which we found actually, we want to look at this data point more accurately because we got a higher RSSI value, but we're not really sure why that is. We need to collect more data. Though chicken wire did a pretty good job of making the RSSI value much worse because it kind of acted like a Faraday cage. We would want to collect more data at different points we would want to collect more data to get a better idea of how this, how each object affects the RSSI values. We tried rotating the cube satellite, but we found that it had a rather minimal difference in the RSSI values that were produced, and we think that is partly due to the fact that Bluetooth on the CubeSat is omnidirectional. And also at this time we had already fully built our cube satellite so we weren't able to test what happens if we were to put objects such as the brackets near the CubeSat. Some potential noise that may occur around the cube satellite would affect the RSSI values would be other Bluetooth signals or even Wi-Fi signals. We did do our testing after school, so there was no one else in the building and we had minimal noise interference. This noise would make the RSSI values more negative and it would make it harder for the CubeSat to communicate with the ground station.
The communication subsystem, measured by RSSI, allows the CubeSat to communicate with the ground station. We will have this finished by the demo day.
This is the data budget for our CubeSat. We took 13 example images to find data, and we found an average image size of about 2.75 megabytes per image. We converted that number to both bytes and bits in order to be able to calculate the bits per pixel in an image. All of our image dimensions were 1920 by 1080 pixels, and we found the average bits per pixel to be about 11.14, although in our calculations we used the value of 12 in order to fully account for all bits in an image. We also wrote a function to be able to calculate the number of bits in an image, the amount of time it takes to downlink an image from the CubeSat to the ground station, and the number of images that could be sent within one potential orbit. This function took the parameters, the height of the image, the width of the image both in pixels, the time in communication between the CubeSat and the ground station in seconds, the data rate between the CubeSat and the ground station, and the number of bits per pixel for the images. We also wrote a function that could calculate the data rate based on the signal-to-noise ratio and the bandwidth. Our example for this program uses a communication time of 600 seconds, a sound-to-noise ratio of 30, and a bandwidth of 1 megahertz. If we run the program, we can see the resulting values are about 24 million bits per image, a downlink time of about 5 seconds per image, and about 119 images able to be sent in one orbit. The data budget plays the important role of facilitating communication between the payload and the ground station. It's particularly important to have it because without it, certain data would become difficult to obtain or unobtainable. To create it, we use data from testing the payload on the ground. Currently, our values were obtained through example photographs and Bluetooth connection. The data budget will be completed before preparation for test day in order to help plan and create the testing process.
Okay, so for our integration and test plan, we have six major steps. So all group members complete their subsystem design, and then we work together to tweak the subsystem designs to make them work together and put them together. And then we all work together to integrate the subsystems completely, and then a full system test with every group member and with every subsystem. And then we work together to figure out the issues between subsystems. So whoever working on like flight software and power, if we have an issue with that, those two people will work together to figure that out, and basically anything like that. And we deploy our CubeSat on the final test day for the final test.